Example 2 of the Systems of Linear Inequalities lab. We have a word problem. The American and British governments want to supply aid to people in an impoverished nation. An airlift will be organized to supply food, clothing, and other supplies. The cargo capacity for the American airplanes is 45,000 cubic feet, and the cargo capacity for the British airplanes is 25,000 cubic feet. The airlift will be limited by the following conditions. 1. The total number of planes used must be 54 or less. 2. The larger American planes require 12 personnel per flight, and the smaller British planes require 6 per flight. 3. The total number of available personnel is 600. To maximize cargo capacity, linear programming will be used. Graph the system of inequalities. Let x equals American and y equals British planes. So, the first thing we're going to do is, from this problem, determine what is our goal. So it seems like our goal is to maximize cargo capacity. So what we're going to do is find our objective function. Our objective function will be about our goal, which is to maximize cargo capacity. So if you look at cargo capacity, we have the cargo capacity for the American airplanes is 45,000 cubic feet, and the cargo capacity for the British airplanes is 25,000 cubic feet. So that means that our cargo, I'll let cargo be z, and this is going to be our objective function, is going to be, for the American airplanes, it's going to be 45,000 times however many American airplanes we have, which is x, because x is our number of American planes. And this is added to our cargo capacity for the British airplanes, which is 25,000, times y, which is the number of British planes. So this is our objective function where z is the cargo capacity, and we want to maximize z. Next, what we're going to do is figure out what constraints we're under. So going back to our problem, we have our constraints. The airlift will be limited by the following conditions. 1, the total number of planes used must be 54 or less. So that's our first condition. So we have our total number of planes is 54 or less. So that will be our x plus y, or our American airplanes plus our British airplanes must be less than 54. So this is x plus y, American airplanes, added to our British airplanes, is less or equal to 54. So that's our first one. We go back for 2. The larger American planes require 12 personnel per flight, and the smaller British planes require 6 per flight. So, and the total number of available personnel is 600. So 2 and 3 go together. So we have, for American planes, they require 12. So we have 12x. And for British airplanes, we have 6 people per flight, 6y, and the total number of personnel is 600. So that's less than or equal to 600. So that's our second condition. The third and fourth condition are not on here, but that's because this is a real problem. In real problems, generally, we're going to assume that we can't have negative amounts of American planes and negative amounts of British airplanes, and we want them to be greater or equal to 0. We don't want them to essentially be greater or equal to 0, so our x is going to be greater or equal to 0, because we can't have negative American airplanes. And same thing goes for our y, because we can't have negative British airplanes. So we are subject to these 4 conditions. And now that we know that, we're going to find our objective function subject to these constraints. So what we need to do is find all the intersections between these functions right here. The easiest way to do that, you could use substitution or elimination to find all these intersection points. In my opinion, the best way to do that is to simply graph these functions. So here we have x is greater than 0, which is everything up here. We have y is greater than 0, so it's everything up here. And we have x plus y is smaller than 54, so that's everything down here. And 2x plus y is equal to 100. Well, that's simply this divided by 6. So this is a simplified, this 2x plus y is smaller than equal to 100 is just a simplified version of this function, this constraint right there. which it's less than everything up here. So we have our four functions graphed into a triangular, but not quite triangular because there's a function right here that goes up like this, that's cut off. And our intersection points are going to be right here, right here, right here, and right here. So we need to find the points, what those are. So this one right here is 50, 0. This one right here is 46 and 8. This one right here is 0, 0, its origin. And this one right here is 0, 54. So we have our four intersection points from our constraints. So what we're going to do is exactly like we did in example 1. We're going to essentially plug in these values for our objective function to find at which point our objective function is at its max, because we know that our min and max will happen within this solution set, and it will happen at one of these intersection points. So we have our points, we have our origin 0, 0, we have 50, 0, we have 0, 54, and we have 46, 8. And we want to substitute them into our equation of z, which was z is equal to 45,000 x plus 25,000 y. So now we get to substituting. For our first point, we have z is equal to 45,000 times 0 plus 25,000 times 0, which is going to be equal to 0. So that will most likely be our min, which means if we had 0 American airplanes and 0 British airplanes, we would have no capacity at all, which makes sense. So for our next one, we have z is equal to 45,000 times 50 plus 25,000 times 0. This is going to be equal to, once we plug it into our calculator, it's going to be equal to 225,000, quite a big number. For our next point, we have z is equal to 45,000 times 0 plus 25,000 times 54. So, and that will be equal to 135,000. For our last point here, we have z is equal to 45,000 times 46 plus 25,000 times 8. And that is going to be equal to 227,000. So we look at each of these numbers and we go, which is our max? Well, it looks to me like 227,000 is our max. So this is our max right here. And that happens when our x is 46 and our y is 8. So we have our max z, or our carrying capacity, our cargo, is at 227,000. So that's the largest amount we can possibly carry with our current constraints. And it happens when we have 46 American planes, because remember X stands for American planes, and 8 British planes. And this is in cubic feet.